C1 as a GCD, we have. Okay, so now I am considering that C1 is a GCD of A and B. Now since C2 is also a GCD, C2 will satisfy the first condition. We have C2 divides C1 because C1 divides A and C1 divides B. What has happened here? You see, I have used the fact that C2 is a GCD of A and B, and that gives me from the first condition that C1 is a GCD of A and B. So that gives me the, or have I written? I am losing track. Okay, sorry about that. I got confused. C2 is a GCD of A and B. So C2 divides both A and B. So that comes from the first condition of GCD, considering C2 in place of C. But C1 is also a GCD of A and B. So if I consider C1 in place of C here, and from these two conditions, I have this C2 divides A and C2 divides B. Now imagine C2 in place of D. Then the fact that C1 is a GCD of A and B forces me to conclude that C2 must divide C1. Hence, okay, or instead of writing hence, I can now run the whole argument with C1 and C2 swapped, the roles of them interchanged. Now, interchanging the roles of C1 and C2, we also have this relation, because now C1 is a GCD of A and B, so C1 will divide both A and B. Now imagine C1 here, C1 divides A, C1 divides B. So C1 will divide a GCD of A and B, which is C2. So that's why C1 divides C2. So from C1 dividing C2 and C2 dividing C1, we get by exercise 2 or exercise 1, I forgot, this is exercise 2, so that was exercise 1. By exercise 1, C1 is equal to plus or minus C2, right? But since C1 and C2 are both positive, we have C1 is equal to C2. We cannot have C1 equal to minus C2, because since C2 is positive, minus C2 will be negative, which cannot be equal to C1, which is positive. So this proves that whenever a GCD of two numbers exists, it has to be unique. Okay, so the question of uniqueness has been taken care of. Now we move on to a notation for the GCD of A and B. Now that there will be one GCD, if at all there is one, so we can formulate a notation. The GCD, see, now we can write the GCD, not a GCD. the GCD of A and B is denoted by this symbol. It looks strange because in most parts of the literature it's written like this, GCD of A and B. But Herstein has decided to not write GCD, and by this ordered pair he wants to mean GCD of A and B. Okay, now having devised the notation, let us now look at some other things. Since we insist that GCD be a positive integer, GCD by definition is a positive integer satisfying two conditions. So since that has been insisted on, we will have GCD of A and B to be equal to GCD of minus A and B, which is equal to GCD of A and minus B, which is equal to GCD of minus A and minus B. Why? It's because since we are concerned about divisors of an integer, after all, greatest common divisor, and the fact that an integer and its negative have the same positive divisors. It's because of that fact that these equalities are coming. Introduction of a negative sign does not change anything about the factors, the positive factors. The positive factors of 12 and those of minus 12 are the same. So that's why we have this. And one more very subtle point, although it's not that important, but still it can be mentioned and should be mentioned, is that the GCD, this function does not depend on the order of the elements. The order does not matter. The definition has nothing related to order. So the definition is symmetric in that sense. So with these things, with these considerations, let us now just look at this GCD of say 60 and minus 24. Since we need not look at negative integers, so this is GCD of 60 and 24, which turns out to be equal to 12. How? Exactly how? The definition in the way it's given, it will not help you much actually finding out the GCD of some given numbers. We will eventually come across a sort of algorithm using the Euclidean algorithm that will help us find the GCD of any two given integers in a very, what to say, you can write a computer program based on that algorithm. Its nature is like that. It can be fed into a machine in the form of a program and then it can be run and that will give you the result. But before going to those parts, let us try to justify the term greatest common divisor. Common divisor, why are we calling it a common divisor? That question is answered by this first condition itself. C is said to be a greatest common divisor if it divides A and B. So it's a common divisor of A and B. But what about this adjective, greatest? To look at that, I give you one simple observation. This is not a result and it's not available in Herstein's book, but it's just a very simple observation. This is, when we write things like this, it's assumed that A and B are integers, they are given to to us, and this is their GCD. This is, okay, by the way, keep one thing in mind. We still have not established anything about whether GCD exists or not. That question will be addressed after this result. Okay, so this is, so I should add whenever it exists is the greatest positive integer that divides both A and B. Let's now have a look at a quick proof of this fact. This will at least justify the use of the word greatest. In what sense is it greatest? So what this result or what this observation seems to say is that if you look at the positive integers that divide A and B, that is the positive common divisors of A and B, then among them this is the greatest. So let's just, I can write proof. Okay, we already know that this is a positive integer and it divides both A and B. It divides A and it divides B. We now have to settle the greatest part. Okay, let K be a, also I should not write in short like that. K be a, it looks ugly. K be a positive integer such that K divides A and K divides B. So K is a positive common divisor of A and B. I have to prove that K is less than or equal to this, because then it's the greatest, right? Okay. Since K is, oh, this will come later. Now K is a common divisor of A and B. So that by the second property of GCD, then K will divide the GCD, right? So A comma B is equal to K times L for some integer L. Now since A comma B is positive by definition, K is positive by our choice, so L also has to be positive. Since L is positive, we have L is a positive integer, so that means it's greater than or equal to 1. 1 is the least positive integer. Hence, A comma B is equal to KL. Using this inequality, multiply both sides of this inequality by K. You have this. So that's how we obtain the fact that a comma b is the greatest among all the positive common divisors of a and b. By the way, do you get the first part of this proof? We already know that this is a positive integer and this come from the very definition of a comma b. Okay, if you go back to that definition, this is nothing but that c. Okay, from there we are getting these facts. So this justifies the use of the adjective greatest common divisor. Now we look at this example in the light of this observation. You see, if I look at the common divisors of 60 which are positive, the divisors of 60 which are positive, what are they? An easy way to write the divisors is, or to find them, is that if your given number is n and c is a divisor, then n by c is also a divisor. So that will give you divisors in pairs. So if 1 is a divisor, then 60 is also a divisor. 2 is a divisor, then 30. For 3 we get 20. For 4 we get 15. For 5 we get 12. For 6 we get 10. 7, 8, 9 don't divide 60. So then 10 divides 60 and the thing repeats. Okay, so these are the positive divisors of 60. Just like that, if we find those of 24, we get 1, 24, 2, 12, 3, 8, 4, 6, and that's all. Now these are the positive divisors of 60 and 24. Now we find the common ones. 1 is there in both the lists. 2, 3, 4, 5 is not there, 6 is there. We have 6 here as well as here. 10 is not there, but we have 12. And that's all. 24 and 8 do not appear here. So these are the common divisors. Among them, 12 is the greatest. 1, 2, 3, 4, 6, and 12. So that's why this is 12. Now, of course, if the sizes of these numbers are extremely large, then this is a highly impractical method to find the GCD. Moreover, we have the question of existence also. We have not addressed the question that whether the GCD exists for any given A and B. Now we will look at that. Okay. But we at least know that whenever it exists, it has to be unique. There is only one special case where GCD does not exist. For every other case, it exists. So we will now come to the first result of this section. Here, however, Herstein chooses to number it quite properly. Lemma 131. He is a whimsical man. Was, unfortunately. So he can do these things. So if at least one of A or B is non-zero, then the GCD of A and B exists. Moreover, but this result says more. Not only that, but this value is expressible in this form. m naught a plus n naught b for some integers m naught and n naught. Okay, so the GCD of two numbers, at least one of which is non-zero, exists and is an integer combination of the numbers. It can be written as a linear combination in this fashion, where the coefficients are integers. We are now going to prove this. And the proof uses the principle of the well-ordering principle. So consider the set M. So what is the set? It is the set of all expressions which look like this, where M and N are integers. By this form of set, we mean the set of integers. Just like by z plus, we meant the set of all positive integers. So this is the set of all integers. So this is a set we have considered. Somehow it's going to help us prove the result. Now, since at least one of A or B is non-zero, we assume without loss of generality that A is non-zero. Say A is non-zero, because since there is no real distinction between A and B, other than the fact that they are integers and one of them is non-zero. So we can assume any one of them is non-zero, so I specifically assume A is non-zero. Look at the use of the word phrase without loss of generality. This will be used very often in mathematics. Although it may not be clear immediately, but the more it is used and the more you see how it's used, you will realize why it is used. The thing is that if someone considers this case and proves the result, then someone goes to the other case where b is not equal to 0, then also proves the result. Looking at those two proofs, he or she will realize that one of them need not be written at all. So in that sense, without loss of generality. Okay, so now what is it that we are trying to achieve? Now, since this is non-zero, two cases arise. Either this is a positive integer or this is a negative integer. If A is positive, then A is equal to 1 times A plus 0 times B belongs to M. Note that A can be written in this form: an integer times A plus an integer times B. So A qualifies to be an element of M. So since A is positive, so we have obtained a positive integer in M. But there is one more case. And that case is when A is negative. If A is negative, then minus A, which can be written as minus 1 times A plus 0 times B, also belongs to M, because M contains all such integers which can be written as integer combinations of A and B. So minus A belongs to M. Now since A is negative, minus A is positive. So in any case M contains a positive integer, that is, the intersection of M with the set of all positive integers is non-empty. Okay, now you look at this set M intersection Z plus. So M intersection Z plus is a non-empty subset of the set of positive integers. It's a subset of Z plus because it's intersection. So from the elementary properties of intersection, we get this fact that this is a subset of Z plus. So by the well-ordering principle, M intersection Z plus has a smallest element C, say. Okay, so C turns out to be the smallest positive integer in M. We claim that this C is the greatest common divisor of A and B. Now we will prove this, and this will definitely establish the existence of the GCD. Okay. Now, to prove this, what do we need to show? We need to show that two conditions are satisfied. The first one is that C divides both A and B, and the second one is that if an integer divides both A and B, then it divides C. Okay. Now, being an element of M, C is of the form C is equal to M naught A plus N naught B. Note that because C is the smallest element of M intersection Z plus, so C in particular belongs to M also. Now, the condition for being in M is that it has to be of this, any element has to be of this form. So in particular, C is also of that form. So for C, we will find some integers M naught and N naught such that that is true. This, we have this relation. Okay. Now, if D divides A and D divides B, if D is an integer that divides both A and B, then by exercise 2, D divides M naught A plus M naught B, which is equal to C. So you can see that here we have actually proved the second condition for C to be the GCD. If D is a common divisor of A and B, then D divides C. We now will prove the first condition that C actually divides both A and B. C is a common divisor of both A and B. Okay. But we will not just prove that, we will prove actually something stronger. Namely the fact that every element of this set M is divisible by C, not just A and B. Next, let X belong to m, x is any element of m, any integer in m, then x must be of the form, then x is equal to, let me write it here, will not be clear otherwise. Then x is equal to ma plus nb for some integers m and n. Okay. Now it's time to make use of the Euclidean algorithm. Now, by the Euclidean algorithm, there exist quotient and remainder integers q and r such that x is equal to qc plus r and r lies between 0 and c in this way. Okay, so we have so-called divided x by c. We have obtained the quotient q and remainder r. The r is non-negative and its size is strictly less than c. Right. Now we are going to use several things. First of all, you look at this. X is ma plus nb. At the same time, x is this also, qc plus r. And at the same time, c is m naught a plus n naught b. So we link all these things, but one at a time. First of all, we equate these two expressions, ma plus nb and qc plus r, because both of them are equal to x. Hence, ma plus nb is equal to x is equal to qc plus r. But this is not where it ends, because in place of c I can use this expression. So this is equal to q times m naught a plus n naught b plus r. Okay. From this we have what do we have from this? See, from this what I am trying to do is that I am trying to write an expression for r by taking all these things on that side. So if I carefully, on that side means on this side. So if I carefully look at them, I have a, I also have b. So r will be, we get, r will be equal to ma minus q m naught a. So that means m minus q m naught times a, just like that. nb minus q n naught b. So plus n minus q n naught b. Now look at this number, this integer. m naught, n naught, q, all these are integers. So from the basic properties of integers, these two things inside the brackets are integers. So that means r is an integer combination of a and b. In other words, r has precisely the form for it to be in the set M, capital M. Hence, r belongs to M. The form of R allows me to conclude that R is an element of M. Now you look at these inequalities. R is an element of M. R is a non-negative integer. C is an element of M, and according to our choice, C is the smallest positive integer in M. So since R is less than C and R is in M, R cannot be positive, because otherwise the smallest positive element of C, that fact is violated. So since R is already in M and it's non-negative and it cannot be positive, so the only possibility is that R has to be equal to 0. Since C is the smallest positive element of M, the inequalities, yes, are less than C, now imply R is equal to 0. But if R is equal to 0, that means X is equal to QC. But then X is equal to QC, or C divides X. Recall what X was. X was any element of M. And we have proved that C divides X, that is the smallest positive integer in M, divides all the elements of M. Or in other words,